Welcome to Beyond the Brackets. Today, let's look into Laurent series. Let C1 and C2 be any two circles centered at A with radii R1 and R2 respectively, where R2 is less than R1. Let Z be any point in the region between the two circles. If f of Z is analytic on C1 and C2 and throughout the region between them, then this expansion is called Laurent series of f of Z. For the first question, we are asked to find the Laurent series expansion of f of z. Before moving with the expansion, we first express the given function in partial fractions. F of z can be written as a by z minus 1 plus b by z minus 2. Taking the LCM and simplifying this, we get z is equal to a into z minus 2 plus b into z minus 1. Putting z is equal to 1 cancels b and we get 1 is equal to a into 1 minus 2. So the value of a is minus 1. Putting z is equal to 2 cancels a and we get 2 is equal to b into 2 minus 1. So the value of b is 2. So the value of f of z is minus 1 by z minus 1 plus 2 by z minus 2. In the first case, we are given modulus of z less than 1. Here, since 1 is greater than modulus of z, we rewrite the terms in geometric series form by taking suitable constants common. Now f of z is, for the first term we get 2 divided by. Here, since 1 is greater than modulus of z, which implies 2 will also be greater than modulus of z. So we take minus 2 common in the denominator to get 1 minus z by 2. For the second term, we get 1 divided by. Since 1 is greater than modulus of z, so taking minus 1 common, we get 1 minus z. For the first term, 2 in the numerator and in the denominator cancels out. Taking the first term to the numerator, we get minus of 1 minus z by 2 whole inverse. For the second term, it will be 1 minus z whole inverse. Using the geometric expansion, 1 minus d inverse, here d will be equal to z by 2. For the first term, we get 1 plus z by 2 plus z by 2 whole square and so on. For the second term, here d is equal to z, so we get 1 plus z square and so on. Writing this in summation form, we have summation. Since the first term is 1 and any number raised to the power 0 will be 1, so the summation starts from 0. Z by 2 power n. So for the first term, when n is equal to 0, we get 1. When n is equal to 1, we get z by 2. And when n is equal to 2, we get z by 2 whole square and so on. In the same way, the second term can be written in the summation form as summation n is from 0 to infinity z power n. So when n is equal to 0, we get 1. When n is equal to 1, we get z. When n is equal to 2, we get z square and so on. For the second condition, we are given modulus of z greater than 2. For the first term, we get 2 divided by. Since modulus of z is greater than 2, we take z common in the denominator to get 1 minus 2 by z. For the second term, we get 1 divided by. Since modulus of z is greater than 2 implies modulus of z will be greater than 1. So taking z common, we get 1 minus 1 by z. Expressing the terms in the inverse form, we get 2 by z into 1 minus 2 by z whole inverse minus 1 by z into 1 minus 1 by z whole inverse. Expanding this using the formula 1 minus d inverse, here d is equal to 2 by z. For the first term, we get 2 by z into 1 plus 2 by z plus 2 by z whole square plus 2 by z whole cube plus so on. For the second term, d is equal to 1 by z, we get minus 1 by z into 1 plus 1 by z plus 1 by z square plus 1 by z cube plus so on. The first term is 2 by z plus 2 by z whole square plus 2 by z whole cube plus so on. And the second term is 1 by z plus 1 by z square plus 1 by z cube plus so on. Expressing this in the summation form, we have summation n is equal to 1 to infinity 2 by z power n. So when n is equal to 1, we have 2 by z. When n is equal to 2, we have 2 by z whole square. When n is equal to 3, we have 2 by z whole cube and so on. For the second term, we have summation n is from 1 to infinity 1 by z power n. So when n is equal to 1, we have 1 by z. For n is equal to 2, we have 1 by z square. For n is equal to 3, we have 1 by z cube and so on. For the last case, we have 1 less than modulus of z less than 2, which implies 1 is less than modulus of z and modulus of z is less than 2. For the first term, we have 2 divided by. Since 2 is greater than modulus of z, we take minus 2 common in the denominator to get 1 minus z by 2. For the second term, we have 1 divided by. Since modulus of z is greater than 1, we take z common to get 1 minus 1 by z. Further, for the first term, 2 in the numerator and in the denominator cancel out. Writing the term in the inverse form, we get 1 minus z by 2 inverse, plus for the second term we have 1 by z into 1 minus 1 by z inverse. Again, expanding using the formula 1 minus d inverse. For the first term, d is z by 2. So we get 1 plus z by 2 plus z by 2 whole square plus z by 2 whole cube and so on. For the second term, d is equal to 1 by z. We get 1 plus 1 by z plus 1 by z square plus so on. So the second term is 1 by z plus 1 by z square plus 1 by z cube plus so on. Writing this in the summation form, for the first term we get n is from 0 to infinity z by 2 whole power n. So when n is equal to 0, the first term is 1. When n is equal to 1, it's z by 2. N is equal to 2 implies z by 2 whole square and so on. For the second term we have summation n is from 1 to infinity 1 by z power n. So when n is equal to 1, we have 1 by z. When n is equal to 2, we have 1 by z square. N is equal to 3, we have 1 by z cube and so on. Here comes the last question. First, finding the value of f of z using partial fractions. F of z can be written as a by z minus 1 plus b by z minus 3 plus c by z plus 2. Simplifying this by taking the LCM, we have z square minus 6z minus 1 is equal to a into z minus 3 into z plus 2 plus b into z minus 1 into z plus 2 plus c into z minus 1 into z minus 3. Putting z is equal to 3 cancels a and c. We get 10 is equal to b into 2 into 5, so the value of b is minus 1. Putting z is equal to 1 cancels b and c to get minus 6 is equal to a into minus 2 into 3, so a will be equal to 1. Putting z is equal to minus 2 cancels a and b, so we get 15 is equal to c into minus 3 into minus 5, so c will be equal to 1, which implies f of z is equal to 1 by z minus 1 minus 1 by z minus 3 plus 1 by z plus 2. Here the region is 3 less than modulus of z plus 2 less than 5. So we express every term in powers of z plus 2. So the terms simplify to, the first term is 1 by z plus 2 minus 3 and the second term is 1 by z plus 2 minus 5. The third term is already in the form z plus 2. For the first term, we get 1 divided by, since modulus of z plus 2 is greater than 3, so we take z plus 2 common in the denominator to get 1 minus 3 by z plus 2. For the second term, we get 1 divided by, since 5 is greater than modulus of z plus 2, so taking minus 5 common in the denominator, we get 1 minus z plus 2 by 5. While the third term is 1 by z plus 2. Writing the terms in the inverse form, for the first term we get 1 by z plus 2 into 1 minus 3 by z plus 2 whole inverse. For the second term it's 1 by 5 into 1 minus z plus 2 by 5 whole inverse. And the third term is 1 by z plus 2. The first term is of the form 1 minus d inverse, where d is equal to 3 by z plus 2. So expanding according to the formula, we get 1 plus 3 by z plus 2 plus 3 by z plus 2 whole square plus so on. Second term is also in the form 1 minus d inverse, where d is equal to z plus 2 by 5. So expanding this, we get 1 plus z plus 2 by 5 plus z plus 2 by 5 whole square plus so on, and the third term is written as usual. Writing this in the summation form, for the first term we have 1 by z plus 2 into summation n is from 0 to infinity 3 by z plus 2 whole power n. So when n is equal to 0, we get 1. When n is equal to 1, it's 3 by z plus 2. When n is equal to 2, it's 3 by z plus 2 whole square and so on. For the second term, we have 1 by 5 summation n is from 0 to infinity z plus 2 by 5 whole power n. When n is equal to 0, we get 1. When n is equal to 1, it's z plus 2 by 5. N is equal to 2 is z plus 2 by 5 whole square and so on. 1 by z plus 2 is common for the first and the third term, which completes the solution for the given question.